In binomial distribution, binomial, just two, isn't it? Now, binomial distribution only constitutes two possibilities. When you see a probability case which is defined by only two possibilities happening a number of times, then that is a binomial distribution. Are you seeing that? Like a case of tossing a coin. When you toss a coin 10 times, are you seeing you only expect two possibilities, either a head or a tail? Meaning out of this experiment, there are only two possible outcomes. Are you seeing that? You get either head or a tail, and you are tossing it 10 times. So 10 defines the number of times of the same thing happening, isn't it? So binomial distribution, there are two possibilities happening n times. Are you seeing that? Like when somebody tells you in a production line, the defective rate is 5%. That is automatically a binomial distribution. Why? Because when you are producing a commodity, whether it is a company producing a mobile phone, when they tell you the defective rate is 5%, meaning you will get either a phone which is defective or a phone which is not defective. So the defective phone will be 5 over 100, 5%, isn't it? And the one which is not defective will be 95 out of 100. Meaning there are only two possibilities, either defective or not defective. So if you produce 100 phones, so 100 is n, denotes the n, the number of times, or the number of those given commodities. Are you seeing that? Are we together? So when you are dealing with a binomial distribution, only two possibilities happening n times, where it is denoted that, so in a binomial distribution, we have p plus q raised to power n. And what were we saying? The whole range of a probability measure, is 1, isn't it? Meaning the whole range of a probability of success plus the probability of failure must give you the whole range of a probability measure. And this is how we were defining a binomial series, isn't it? Can you remember the binomial theorem? So it means the whole range, p plus q raised to power n, should give you the whole range of a probability measure 1. Are you seeing that? Where this p, we will use it to denote the probability of success, and the q, we will use it to denote the probability of failure. And we are going to see which value should we always choose to be p, and which value should we always choose to be q. Because cases of binomial distribution are always used to approximate, the Poisson distribution is used to approximate the binomial. Are you seeing that? So we are going to check an instance to use a Poisson distribution to approximate a binomial. And that is only going to happen if you are making what to choose for p. Because when you make a wrong choice for p, you will find that you cannot approximate it with the Poisson. Are you seeing that? Are we together? Yes. So, you can recall from the binomial series, when you are expanding this, when you are expanding p plus q raised to power n. If you are expanding this, see, you are using the combinatorics. The first one, the power is n, isn't it? Yes. So it is n combination 0. That was the first one, isn't it? Yes. N combination 0, then we have p of 0, then q is now n minus 0. Are we together? See, one power was ascending and the other one was descending. Yes. Are we together? Yes. Then the next one is n combination 1, then it is now this one p of 1, isn't it? Then q is n minus 1 power is ascending, 1 power is descending. Then you move on, it is plus n combination 2, then p raised to power, then q raised to power n minus 2, isn't it? Then plus n combination p raised to power, then n, q raised to power n minus, then you move until the end. Once you reach the end, the whole of that probability measure is supposed to be 1. So it is like saying when you have maybe x plus 3 raised to power 2. Are you seeing this? See, this is binomial. See, this means the n is 2 combination 0, then x raised to power 0, 3 raised to power 2 minus 0. Isn't it? That's how to deal with binomial. Then the next one, it is 2 combination 1, x raised to power 1, then you 3 raised to power 2 minus 1. Until you reach the last one, isn't it? Good. Now, we've seen how to expand a binomial problem. Now this, remember this combinatorics is what you were using to define a binomial series when n is not a natural number. But in case of probability, n is always a natural number, meaning we just need the combinatorics, not the binomial series in terms of factorials, isn't it? Because you can remember in terms of factorial, you found that n combination r was given by n factorial over r factorial n minus 1 factorial. So that is a case when n is not a natural number, but in probability, n is the number of times must be a positive natural number, so we don't need the factorial for the binomial series, isn't it? Are we together? Good. So, now look at this. Look at this. If you now look at this, you will see the power defines. Remember when you are dealing with binomials, success and no success. So if you say P is success and Q is failure, then you will be asked, the power of P dictates the number of outcomes. Are you seeing that? So when you say no success, meaning the no means zero, isn't it? So when you say no success, you take a term which the power of P is zero because P is defining success. Are you getting the definition? When you are looking for no failure, meaning you take a term where the power of Q is zero. Are you getting the argument? Because that term is what defines no failure. But now if you go back to probabilities, the mutually exclusive events and the addition laws of probabilities, or the independent events and the multiplication laws of probabilities, what are you seeing? You are seeing in the addition laws of probability, the word or is defining plus, isn't it? So it means when you say this a plus, it means or. So it means this, or this, or this, or this, or up to the end gives you a total of 1. Are you seeing that? So when somebody tells you what is the probability of getting, if P is defective and Q not defective, what is the probability of getting at least 2 defectives, meaning a minimum of 2 defectives, and P is denoting defective. Are you seeing that? At least 2 meaning 2 onwards. Are you seeing that? So it means when the power of P is 2 or 3 or 4 or 5. Are you seeing how to get those terms? Are we together? Is that understood? So let us now see we want to define it with P. So no outcome, the probability no outcome, the probability of no outcome implies what? It implies the term which has P to power 0. So for you to get a probability of no outcome is this term where the power of P is 0 when we're dealing with success. Are you seeing that? So that is n combination 0, P of 0, Q of n minus 1. The whole of that term means no outcome when our reference is P. Are we together? When our reference is P. So this term defines no outcome. Then exactly, what about exactly one outcome? Which term defines one outcome? Our reference in P in this case. Are we together? So one outcome, it means the power of P is 1. Are you seeing that? Yes. Which term is having a power of P is 1? So it is the second term. So exactly one outcome is n combination 1, P of 1, Q minus 1. Are you seeing that? Exactly 1. Then? The first outcome, Q to n minus 0. This is n minus 0. Oh, I wrote here, oh, sorry for that. N minus 0. Then you move to the next one, isn't it? Exactly. We are done with exactly one outcome. What about exactly 2 outcomes? Which term is defining exactly 2 outcomes? When the power of P is 2, when we are putting P to be the reference in this case. Are we together? So exactly 2 outcomes. See, this is the term which is having a power of P is to be 2. Because this addition means or, isn't it? Are we together? So exactly 2 outcomes is going to be what? N combination 2, P raised to power 2, Q raised to power n minus 2, isn't it? Are we together? Exactly 3 outcomes. Exactly 3 outcomes will be the fourth one. The fourth one, which is P is power 3, isn't it? Good. That is n combination 3, P raised to power 3, Q into n minus. So it means for you to solve any problem in binomial distribution, you must get these exact outcomes first before you answer anything. Because the things they will ask you is something like at least, at most, and you cannot get those at least or at most without getting these exact probabilities, isn't it? So it means the moment somebody can come and tell you what is the probability of getting at most 2 outcomes. Do you see that? So when I come and say at most 2 outcomes. Now look at this statement. At most means the maximum you can reach is 2, isn't it? So at most 2 outcome means what? Either no outcome, or 1 outcome, or 2 outcomes. So that is at most 2. Yes. At most 2 meaning you can get 0, or 1, or 2, isn't it? And at least 2 means 2 on 1, isn't it? So at least 2 it means either it is a 2, or 3, or 4, or 5, isn't it? Are we together? So the word at most 2, at most, what is that? At most 2 outcomes will mean either 0 or 1 outcome or 2 outcomes. Then you substitute. What is exactly 0 outcome? No outcome. What is defining no outcome? N combination 0, P of 0, Q n minus 0. The word or plus exactly 1 outcome. What is defining 1 outcome? N combination 1, P of 0, Q, P of 1, n minus 1. Or, what is defining 2 outcomes? N combination 2, P of 2, Q, n minus. Are you seeing you now define at most 2 outcomes? Are you seeing that? It is these exacts which are giving you the definition. Are you seeing that? Are we together? Now, look at a case. Now, what about when they now talk about a case like at least? At least 2 outcomes. So if it is at least outcome, and maybe your n is 2000, at least 2 outcome will be either 2 or 3 or 4 or 5 or 6 up to 2000. Will you write all those? No. But you know, the whole of this is equals to 1, isn't it? So when you are looking for at least 2 outcomes, it means what? It means either, remember you have from 0 or 1 or 2 or 3 or 4 or 5 or until the end, then the whole of that is equals to 1, isn't it? But at least 2 outcomes means 2 onwards, isn't it? It means you are starting from 2 or 3 or 5 up to this end, isn't it? So for you to get from 2 up to this end, what does it mean? So it means you remove this part. So you move 1 or 0 or 1. If you remove it, so you take it on the other side of the bracket. So if you take 0 or 1, so it is 1 minus 0 or 1. Are you seeing? Then you've removed it on this side of the equation. So you see on this side you have at least 2, isn't it? 2 onwards, 2 or 3 or 4 or 5, because the whole of it was equals to 1. Are you seeing? So at least 2, instead of getting all this, because n may be a very big number, isn't it? So you simply get 1 minus the remainder. What was remaining this side, isn't it? 1 minus 0 or 1. Have you seen how I've done that? Yes. Are we together? Yes. So getting at least 2, the side, in any probability you are looking here has 2 sides. Meaning when you're dealing with at least 2, you have at least 2 and at most 1. When you add them, you get the whole 1, isn't it? So instead of working for at least 2, why don't you work for this at most 1, then you subtract it for 1 to get the otherwise, isn't it? So you can remember from probability 1, we say that the probability, the range of probability measure is 1, meaning the probability of an event occurring minus the plus the probability of event not occurring must add up to 1, isn't it? So otherwise, 1 minus the otherwise gives you what you are looking for, isn't it? So the otherwise of at most 2 is, of at least 2 is at most 1, isn't it? Are we together? Very good. So that is how to deal with the binomial distribution. Now, having seen how to deal with the binomial distribution, there's now how do we find the mean and the variance of a binomial distribution, isn't it? Are we together? Now the mean of a binomial distribution is given by NP, n times the probability of success. The mean of a binomial distribution is given by NP. Is that okay? That is how to find the mean of a binomial distribution. Then the variance of a binomial distribution. The variance of a binomial distribution is given by NPQ. The product of the three now gives you the variance. Is that okay?
Yes.
The mean is NP and the variance is NPQ. Is that okay? So that is how to deal with the binomial distribution. Let us see a first example under this.